Isn't it interesting that solutions of substances in water come in all of the colours right across the whole of the visible spectrum? You get red ones, we can get green ones, yellowy green, we get blue ones, we get all sorts of colours, and we can get colourless ones, no colour at all. So how do we explain these colours? Why does the solution appear red to us or appear blue to us? Well, the simple explanation is that we're looking through that solution, and everything that's coming in the other side, hitting that solution, is white light, consisting of all the wavelengths of the whole of the rainbow. And as the light comes through and hits our eye, some of the wavelengths are selectively absorbed, leaving only red ones to come through, and it's only those wavelengths that affect our eyes in the sense that we see red are the ones we see. And in this particular case, all the colours of the rainbow are incident, striking, coming into the solution from behind. In this case, only some of the wavelengths are absorbed, and the ones that are left behind are the ones that we see as blue. Now, in particular, in a red solution, it must be that the wavelengths being absorbed are those at the red end of the spectrum. That's the high energy end of the spectrum, absorbing blue and violet and transmitting those that are red. In the case of the blue, it makes sense if whatever's in the solution, the molecules are interacting with the light coming in, and the molecules in that solution are absorbing wavelengths up at the red end of the spectrum and only letting through stuff that we recognise as blue light. Now, I have up on the screen here an absorption spectrum over a range of wavelengths where the molecules in this solution absorb, and you'll see it as up on the screen here. Here's the absorption spectrum of methyl orange solution, which is reddish orange in acidic solution. The visible spectrum stretches from about 400 nanometers, the violet high frequency end, up to about 750, the red end. So the visible spectrum goes way to the right of what's shown in this graph. So what's absorbed mainly is about 470 nanometers. It's clearly in the blue part of the spectrum. And if blue light is absorbed from white light, only the red and orange passes through, and it appears red-orange to us. By comparison, here's an absorption spectrum of a copper sulfate solution. Blue, perhaps blue-green. It absorbs mainly about 700 nanometers and beyond. That's the red, and the infrared. As far as our eyes are concerned, what's absorbed in the infrared doesn't matter, but if the red is taken out of white light, then only the bluish colour is transmitted, and that's what we see. Right. I hope that makes sense. Now, all the solutions that are blue are not the same blue. Different substances have molecules that absorb different regions of the red, and therefore are transmitting different, similar but not identical wavelengths at the blue end. And why is a solution of, this is potassium chloride salt, why is that colourless? Well, I think the answer to that is simple, is that it contains no species, neither potassium ions nor chloride ions, interact with light in such a way that they absorb wavelengths which are in the visible region and take out some of the wavelengths, leaving us with the others. So there's been no subtraction of some wavelengths by any species that's in this solution. Now, why are some substances coloured? Now we come to the fascinating, absolutely fascinating explanation that the energy that electrons can have in whatever molecules are doing this absorbing, the energy that electrons can have is quantized. They can only have certain levels of energy. Let me get these out of the way. Just imagine if our energy was quantized, that we could only walk at 1.3 kilometres per hour, or 1.9, or 2.7, or 3.1, and no speed in between. Or we could only talk at this pace, but not faster than that or slower than that, unless we go to this pace, but no faster than that or slower than that, unless we go to this pace, but no pace in between. That's quite a remarkable thing, which only 120 years ago caused enormous storm in the scientific community when Niels Bohr and a few others suggested that that be the case, rather than just continuous energy. That was almost too much to deal with. So what we have in any species that's absorbing light is that they have energy of electrons. It's a simple matter in atoms, particularly hydrogen atoms with only one electron. It's more complex in molecules. There are many, many levels, but conceptually, these are the energy levels. This is not distance, this is amount of energy that electrons have and can only have. Cannot have energy that value, nor that value, nor that value, nor that value, nor that, nor that. Only that's possible, that's possible, that's possible, that's possible. And this molecule, ion, whatever, is in solution, and in comes some light with a whole range of wavelengths or a whole range of energies of quanta, and it says, pew, I don't like you because if I absorbed you, it would take me to there, and I can't exist in that condition. If I absorbed you, I can't do that because it would take me to there, and I can't exist in that condition. I will only interact with and take out quanta whose energy exactly corresponds to a jump like that, or a jump of my energy like that, or a jump of my energy like that, or like that, some of these. Specifically those quanta. And it turns out that these spacings for some substances happen to be about equivalent to the wavelengths of visible light. Let me make this clear. The energy of a photon that is absorbed, sorry about that writing, is equal to the delta E, the difference between levels. So I can have a photon absorbed whose energy is exactly that, or whose energy is exactly that, or another photon whose energy is exactly that, and so on. But no others in between. And if these ones that are being absorbed happen to be in the reddish region, as they sometimes are, then we have a blue solution. I've come outside for this little segment, which I admit to being an afterthought, to talk about in the context of absorption of light, partial absorption of light by species to give us coloured solutions in a slightly different way. I need the white light from the sun, which is pouring in here and going onto this white base. If I put up an opaque object like a book here, I get a shadow. Total elimination of all of that light from reaching there. None of that white light is reaching there, shadow. I can physically create a partial shadow with this scientific object called a sieve, used in cooking. It has steel wires, and if I hold that there, some of the white light coming down doesn't reach the base because it's physically obstructed. But the white light that does reach the base is the same nature as that hitting there. It's just that some of it is physically obstructed, but a partial shadow. I can create a partial shadow in a chemical way, which is quite different. Here's a partial shadow being produced chemically. It's a partial red shadow, which is due to the fact that from the white light, some of it is not transmitted. In this particular case, selectively, blue and green wavelengths or photons that correspond with light of blue and green colours are eliminated and only the red passes through. So some of the light is passing through, it's a partial shadow and it's a partial red shadow. In this particular case, another partial shadow, a yellow shadow, caused by absorption of which wavelengths or which photons. And here's another one, blue partial shadow caused by elimination or absorption of some of the white light not getting through there. So, and some is. A partial shadow produced chemically, all due to the fact that the energies of the electrons of the species in here are quantized, only have certain energy values, and in jumping from one level to the other, that can only happen for photons of particular wavelengths, which in this case happen to correspond with, say, around the yellow-orange part of the visible spectrum. Simple but powerful little ideas.